And yeah, today I'll be talking about the problem of Byzantine distributed QCD, and this is a joint work with Shi Junling and Jay Huang. Okay. All right. So this talk will consist of two parts. In the first part, I'll talk about the problem of the quick exchange detection, or QCD, and in the second part, I'll talk about the Byzantine version of this QCD. All right. So before I talk about the QCD, let me first review the binary hypothesis testing. And yeah, so in this binary hypothesis testing, we have two hypotheses, H0 and H1, to be tested. And we know that one of them is true, okay? And we make NIID observations according to these distributions. So yeah, so that is, if H0 is true, then our samples are IID from P0, and if H1 is true, then our samples are IID from P1. Okay, and after we observe these NIID observations, we make a decision H hat here. Okay, and there are two error events associated with this decision. Okay, so the first one is the false alarm. That means given that the underlying hypothesis is H0 and our decision is H1, and the second error event is called a misdetection. So that is given that the underlying true hypothesis is H1 and our decision is H0. Okay, and here the goal here is to minimize the probability of misdetection subject to a constraint on the probability of false alarm. And in 1933, Niemann and Pearson, they showed that for this binary hypothesis testing, for this setting, the error test is optimal. Okay, so that is, we declare the H1 is true if the error is bigger than the threshold H. And this threshold H is computed such that this constraint on the probability of false alarm is met with equality. Okay, so that's the Niemann-Pearson setting of the binary hypothesis testing. Okay, we know that there are tons of applications for this binary hypothesis testing, but one issue here is that this is an offline setting. Okay, so we know that in many applications, this means a disaster, right? So this brings us to study the QCD. Okay, so there are three main features of the QCD. Okay, so the first one is that, so the first one is that the world is sequential, not blockwise, right? So the events may happen at any time, not the beginning of each block. Okay, so that's the first feature. And the second feature here is that in many applications, we are forced to make online decision. So that means we don't actually have the luxury to wait until the very end of the block. Okay, and the third feature here is that in many applications, the latency and delay matter. Okay, so there are the main features here. Okay, so the first one is that there is no sense of block, and we make online decision, and the latency and delay matter. Okay, so yeah, those are the features of the QCD. All right, so now let me formally state the problem of the QCD. Okay, so here we are detecting the occurrence of an event happening at the unknown time v. Okay, and yeah, so our samples are sequential. Okay, and our samples are IID according to P0 if t is before v, and the P1 if t is at after v. Okay, so those are our samples, and suppose we declare that the change has already happened at the time t. Okay, then again there are two events associated with this t. Okay, so the first one is called the delay. So that is, if your t here is after v, then we define the delay to be the time here. Okay, so that is t minus v, and if your t is before v, then our delay is set to be 0. Okay, so that's why I have the plus sign here. So that means we take the maximum between 0 and this number t minus v here. Okay, and we use this metric to measure the performance of this t. Okay, so that is we just average of the delay here t minus v plus, and then yeah. So here, since we are considering the worst case, so we take the essential soup over the pre-change observation here, and then take the soup over all the possible v. Okay, so yeah, so yeah, this is our first metric, and for the second event, that is the false alarm. So that means our t is before v. Okay, so here we use the mean time to a false alarm here to measure the performance of this t. Okay, and by the way, here I use the subscript v here to denote that the underlying distribution is P0 before V and P1 after. Okay, so here this means that this means that we assume that the change never happens. Okay, so basically this mean time to a false alarm measures on average the time duration until we see the first false alarm. All right, so here we want the delay to be small and the mean time to a false alarm to be large. So the goal here is to minimize the delay subject to a constraint on the mean time to a false alarm, gamma. Okay, yeah, so this problem was first studied by Lorden in 1971. Okay, and in that paper, he also discussed a procedure to make the decision. Okay, so that's called a cumulative sum or CUSUM procedure. So in this CUSUM procedure, we basically declare the event has happened at the first time t such that this yt is bigger than the threshold. Okay, and this yt is called a CUSUM statistic, and that is computed this way. And you can see that here we are simply accumulating the LLR here. Okay, so you can see that this CUSUM procedure is very similar to the LLR test, but the only difference here is that we put the plus sign here. So that means this CUSUM statistics is never negative. Okay, yeah. So this plus means that we take the maximum between 0 and this value. Okay, so that means if this value is negative, then we just set yt to be 0. Okay, so that's the only difference between the CUSUM procedure and the LLR test. And also, you can see that this is a sequential version. Okay. All right. So in that paper, Lorden showed that this CUSUM procedure is asymptotically optimal, and that can achieve the best trade-off between the delay and the mean time to a false alarm. Okay. So the scaling is like this. Okay. So it says that the delay scales like log gamma divided by I. So here the I here is the Carrier divergence between these two distribution, and gamma is the constraint on the mean time to a false alarm. Okay, so that's the results by Lorden. And later on in 1986, it is shown that this CUSUM is this CUSUM procedure is in fact optimal. All right, so these are the classical results from QCD. And here's one example. So in this example, I set the V to be 500 here. And before that, my samples are IID from Gaussian with 0 mean and variance 1. And after that, my samples are from Gaussian with mean 0.1 and variance 1. You can see that from this figure, it is hard to tell where the change happens, right? But here, yeah, so yeah, so if we plot the CUSUM statistics, you can see that the CUSUM statistics starts to rise after 500. Okay, and these black bars here means the threshold I set. Okay, so you can see that. Yeah, so you can see that there's a trade-off between the between the two metrics. So if we set the threshold to be small, that means it is more likely to have false alarm like here. And if I set the threshold to be large, then that means my delay might be large. Okay, so there's a trade-off. But in these results, they show that if we set the threshold h here such that the constraint on the mean time to a false alarm is met with equality, then the trade-off is optimal. Okay, yeah, so this is the first part of this talk. All right, so now, yeah, let's talk about the problem of the Byzantine distributed QCD, and this is based on the yeah. So this part is based on these papers. Okay. Okay, so our main motivation here is that in IoT scenarios, we know that those tasks are usually carried out by a bunch of distributed sensors, and the sensors are cheap and prone to be compromised. Okay, so that's the scenario. And also, like in smart grids, we know that the power networks, they are very sensitive to power quality events or PQ events. But this is not a problem in traditional power network, because in traditional networks, your device are stable and your power source are also stable. But in smart grids, your source may not be that stable, and also your device may be cheap or something. So in this smart grids, the how to quickly detect the PQ events are very critical. Okay, so that's our main motivation here. Okay, so yeah, this brings us to study the distributed version of the QCD. So that means we have a fusion center who wants to monitor an event through a bunch of sensors. They are distributed. Okay, so yeah, so now in this problem, the sensors they make their own observations according to this distribution. Okay, and yeah, and there are IID across the sensors. And we have a starting rule T, but now this T consists of two parts. In the first part, each sensor they have their local rule, and then they can feedback their report to the fusion center via a noiseless link. But the links may subject to a bandwidth constraint. Okay, and the fusion center they will make the global decision based on the local local reports he has received. Okay, and again we can define the two performance metric. That is the first one is the delay, and then like this, and the second one is the mean time to a false alarm like this. Okay, so you can see that this is pretty much the same with the QCD, but the only difference here is that now our task is carried out through a bunch of sensors, right? So now we have to condition on all the pre-change observations, and they are vectors like here, and also your T has these two parts, right? So that's a function of both the local reports and the fusion rule. Okay, so that's the difference between this distributed version and the traditional QCD. All right, so now, yeah, so here is the more advanced version that is called the Byzantine distributed QCD or BDQCD. Okay, so in BDQCD, again, we have a fusion center, and he wants to monitor an event through a bunch of sensors, but we know that some sensors are compromised. Okay, so here I assume that there are n sensors, they are honest, and m of them are compromised. Okay, and yeah, and yeah, so here we assume that again for the n honest sensor, they follow the stopping rule T, and for this m compromised sensor, they can do whatever they want. Okay, so they can form a tag. Okay. Yeah. Any question? Okay. All right. So this n compromised sensor, they can do whatever they want. Okay. So I just call their strategy G here. Okay. So that means they can corroborate or coordinate. Okay. And again, we can define two metric here, delay and the mean time to a false alarm. Okay, you can see that the difference between this one and this one is that now we have to, okay, so now since we are considering the worst case, so we take the soup over all the G here, and we take the inf here. Okay, because the compromise sensor would like to make the delay larger, and would like to make the mean time to a false alarm smaller, right? And this is the worst case, so we have to take soup here and if here.
Do you know what the set G is? Sorry to interrupt. This is Paris too.
Sorry, say it again.
Do you know what the set G is?
No, we don't. So yeah, so basically they can do whatever they want. We don't have the control over the G, and we don't know it. Yeah. Okay. Any other question? All right. So the goal here is to minimize the delay subject to a constraint to the mean time to a false alarm. Okay. So that's the problem we are studying. All right, so the question we want to answer and the question we try to ask and answer is that I want to know the optimum scaling rule for this problem. Okay, so that is we want to know that for an optimum T, that is the stopping rule, how does the delay scale with the mean time to a false alarm? Okay, and yeah, we know that some partial results, right? For the QCD, I just mentioned that the scaling is like this. Okay, so that is log gamma divided by the divergence I here. And for the yeah, so for this distributed QCD, there's a paper by May in 2005. He shows that the optimum scaling is log gamma divided by Ni. So N is the number of sensors here. Okay, so you can see that this is as if the problem is completely centralized. Okay, because if the problem is centralized, then the fusion center will get all the X here, right? So basically, we can just transform the problem into a traditional QCD with the I become N times of I. Okay, so yeah, so in this paper, he shows that we can achieve this, and moreover, he shows that this can be achieved by 1-bit links. So that means the bandwidth constraint for each sensor to the fusion center is just 1 bit. Okay, so here's how he does that. Okay, so in this paper, yeah, so here's the rule that the sensors they just do their their CUSUM procedure locally, and then when the CUSUM statistic is bigger than the threshold, they say yes, okay, and the fusion center will declare the event happens when all the sensors say yes, okay, and he managed to show that this is asymptotically optimal. All right, so now the question we try to ask is that how about the BDQCD? Okay, so what's the best scaling for this problem? And yeah, so in 2018, there's a paper here. They have provided some starting rules, and that they achieve this scaling. Okay, so the first rule is called the D low sum Q sum. Okay, so in this D low sum Q sum, the honest sensor, they constantly report the CUSUM statistics. Okay, so you can see that this is not critical because your CUSUM statistics can be any real numbers, right? So that requires a larger bandwidth, right? So that's not critical. Okay, and the fusion center merge D lowest CUSUM statistics. Okay, so D is an integer. All right, so yeah, so the reason that this rule only merge D of them, not all the reports, is because that is because like here some sensors are compromised, right? So if we merge all the CUSUM statistics, then the compromised sensor can send a very large number and trigger the false alarm. Okay, so this is why they just pick D reports to merge. Okay, and this D here is a parameter to be designed. Okay, all right, and the second rule here is called the D voting rule. So that's pretty much an extension of this rule. Okay. So basically, he just let the sensors do their local CUSUM and report yes or no. Okay, and then the fusion center will declare the thing has happened if D of them say yes simultaneously. Okay, and again, the D here is something we can design. Okay, and they show that both the D low sum CUSUM and the D voting rule, they achieve the same scaling of this. Okay, so that is log gamma divided by D minus M times I. And then D can be anything in this set. All right, so you can see that the best scaling is that we set D equal to N, and that will shows that this scaling is possible. Okay, so the question here is that is this optimal scaling? Okay, and we don't know because there is no converse for this problem. Okay, yeah. So our first contribution here is that we show a tight converse. Okay, so by tight converse, I mean that we show that for any decision rule T with the mean time to a false alarm bigger than gamma, then the delay should scale no slower than this value. Okay, so we can see that this is exactly the same as this one. Okay, so combining these results and our converse, we show that for BDQCD, the optimum first order scaling is this one. Okay, and moreover, since this rule, since this delay can be achieved by the D voting rule, okay, and here D voting rule only requires 1 bit bandwidth constraint, right? So that means this the optimum first order scaling can be achieved by 1 bit links. Okay, yeah. So yeah, this is our first contribution, and in the following, I'll talk about the how to prove this type converse. All right, so here is the schedule of the proof. All right, so in our proof, there are three main ideas. Okay, so the first one is that we realize that since we're proving a lower bound, so we don't actually need to find the best G. Okay, so this, yeah, so this gets back to Wan Cheng's question that do we know the G? So yeah, so here, although the D and the A are defined for the best G, right? But here we don't actually need to know the best G, okay? Because here we're proving a converse, okay? So any stronger attack will only make the delay larger, okay? So our first idea is that we don't actually need to know the best G, we just need to find a good one. Okay, so according to this idea, we construct a attack called a reverse attack. Okay, so this, yeah, okay, so our problem is the BDQCD, right? So after this idea of this, we show that our the performance of this BDQCD can be lower bounded by this BDQCD with a specific attack. Okay. All right. So the second idea here here is that we introduce a not too powerful genie. Okay. So you can see that I highlight the not too powerful because it is easy to get a meaningful lower bound by saying that suppose there's a genie who reveals the identity of the compromised sensor to the fusion center, right? Then the fusion center can just ignore those sensors. But it turns out that this genie is way too powerful. Okay, so we introduce a genie that is not so powerful. Okay, and so yeah, this makes us to here. Okay, so we know that this genie-added BDQCD will serve as a lower bound for this, and that will serve as a lower bound for this. Okay, and our third idea is that we transform the problem into a traditional QCD, and this is inspired by the idea in this paper, in this paper by Wei-Ning Chen and Yishan Wang. Okay, yeah. So after this, we know that this will serve as a lower bound for this, and since this is a traditional QCD, right? So we know we can achieve the optimum by using the CUSUM procedure. Okay, so after that, we just use the CUSUM procedure to compute the delay scaling, and that will be a lower bound for this, and for this. Okay, so this is the sketch of the proof. All right, so now let's go into the details. So yeah, the first idea again is to realize that we don't actually need to know the best G. So we find we construct a G called the reverse attack. So that is we let each compromised sensor generates IID fake observation. Okay, and then these fake observations are from this distribution. Okay, so you can see that I didn't actually do anything, right? I just swap the P0 and P1. Okay, so that means if the event has not happened, the fake observations are IID from IID from P1, and if the event happens, then the fake observations are IID from P0. Okay, so I just swap the distribution. Okay, and yeah, and then after this, the compromised sensor generate the reports based on this fake observation. Okay, yeah. So one question here is that, is this good enough? Okay, and yeah, because I just mentioned that the compromised sensor they can corroborate and coordinate, right? But here we seems to give away the corroboration here, right? Because the compromised sensor they just generate their reports according to this IID fake observation. Okay, but yeah, it turns out that so it turns out that this is good enough for us to prove the converse. Okay, yeah. So in the following, I will assume that the compromised sensor they always follow this attack. Okay, so the second idea here is that to introduce a not too powerful genie, right? So we construct a genie that reveals the observations here, X, that is used for generating the local reports for all the K. Okay, so that means for the honest sensor, they just, the genie just tell the fusion center their XT, and for the compromised sensor, they just tell the genie just tells the fusion center the fake observation. Okay, so yeah, and after that, the genie also reveals the identity of the n minus m honest sensors. Okay, so here is one example. Here we have total n, that is 4. Okay, so we have 4 honest sensor, 1, 2, 3, 4, and we have 2 compromised sensor. And the genie reveals the locations of these n minus 4 and it's 2 honest sensor to the fusion center. Okay, so this will make the problem like this. Okay, so we have total n minus m honest and revealed sensors, and we have m honest sensor and m compromised sensor that we don't know the identities. Okay, so this is the problem after the genie. All right, and yeah, so in the following, I will show that their contributions will be cancelled out. Okay, so that will make the problem distributed QCD without a compromised sensor with n minus m sensors. Okay, so you can see that this will give you the true scaling. Okay, so that is log gamma divided by n minus m times I. Okay, because their contribution will cancel off. Okay, so that's the yeah. So that is shown here. Okay, so we first define a function S that will assign the first 2M sensors the type. Okay, and the type 1 means that we think the sensor is honest, and type 2 means that we think the sensor is compromised. And yeah, so there are exactly m of them will be assigned to type 1, and the other sensors will be assigned to type 2. All right, so we let S be such a function, and we let this calligraphic S to be the collection of all the S. Okay, and for each S, that will induce a probability distribution like this. Okay, and okay, yeah. So the so this p theta sk is here. Okay, so you can see that if S of k is 1, then that means we think the k sensor is honest, right? So that makes p theta 1 equal to p theta. And if S of k is 2, that means we think the sensor is compromised. So that makes p theta 2 equal to p theta bar. Okay, so this is because we define the compromised sensor to adopt this attack. Okay, so basically we just swap the distribution, right? So this will make p theta 2 equal to p theta bar. Okay. All right. So here is one example, and in the so here in this part, we assume that the S is 1, 2, 2, 1. So that means we think the first sensor is honest, second one is compromised and honest. Okay, and under theta equal to 0. Okay, so so 0 means that the event has not happened, right? So under theta equal to 0, our samples are gonna follow this distribution. Okay, so that is p0 x1 times p1 x2 times p1 x3 times p0 x4, and that's two. They are always honest, right? So that's p0 x5 and p0 x6. Okay, so this is one example of this p theta s. And here's another example. That is, we assume that the s is 2, 1, 1, 2. So that means we think the first sensor is compromised and the second is honest, and compromised. Okay, so under theta equal to 1, then we will have p0, p1, p1, p0 times p1, p1. Okay, all right. So this is another example, and so I choose this example specifically for a later use, but let's not talk about it now. Okay, all right. So for this problem, so after the Gini, we can again define the delay and the mean time to a false alarm. Okay, and you can see that in the beginning, sorry, where is? Okay, so here you can see that this is how we define the delay and the mean time to a false alarm for the original BDQCD, right? So we take the sup over order G and we take the inf over order G for the mean time to a false alarm. But after all this, you can see that we already know how the compromised sensor behave, right? So that means the only thing we don't know about the compromised sensor is their identities. Okay, so we can replace the sup over G to be sup over S, and here similarly here. Okay, because that's the only thing I don't know about the compromised sensor. All right, so that's the Gini-added BDQCD. And we know that this will serve as a lower bound for the original BDQCD. All right, so now let's come to the third idea. That is, we do the transformation. Okay, so we define this tau 2m to be the ordering map that will put the non-revealed 2m entries in descending orders. Okay, so it's like this. So just recall that we have total n plus m observations, but we know that the n minus m of them are honest, right? So we don't care about those parts, but for the other 2m parts that we don't know the identities, we just put them in the descending orders. Okay, so that's what this function tau 2m does. Okay, and we define the p theta tilde to be something like this. Okay, so that is we just summing over all the p theta s of xt, and we summing over all the xt such that after this tau 2m map, they will become the same x tilde. Okay, so in other words, we can so you can think of it this way, that we fix the x tilde and summing over all the tau, all the 2m permutation, right? So so this is basically that. Okay, so we fix and so we fix an x and summing over all the permutations. Okay, and one important thing here is that this is no longer dependent on S. Okay, why? Because you can see that let's use this example to see that. Okay, so under for the first part, let's say the S is 1, 2. So that means we think the first one is honest, second one is compromised, right? So under theta equal to 0, and we have to summing over all the permutations of these x1 and x2, right? So that that corresponds to p0 x1, p1 x2 times p0 x3 plus p0 x2, right? Because because here we have to sum over all the permutations for the first two entries, right? So plus p0 x2 times p1 x1 times p0 x3. And here for this assignment 2, 1, again we can do the same thing. So under theta equal to 0, the PDF is p1 x1 times p0 x3, p0 x2 times p0 x3 plus p1 x2 times p0 x1 times p0 x3. So you can see that this part is the same as this part, and this part is same as this part. So this is independent of S. Okay, so yeah, and this is good because we can finally get rid of the compromise sensor, right? Because after the Gini, I just say that the problem depends on the compromise sensor only through this S. But here, for this problem, we don't have that S anymore because the problem is independent of S. Okay, so for this transform QCD, the delay and the mean time to a false alarm are just like this, and that's the traditional QCD with this PDF. Okay, but here I haven't connect the transform QCD with our BDQCD, right? So here is the connection. We can show that. Okay, so first of all, all right, so first of all, a rule T is said to be symmetric if it doesn't matter how we permute the X. Okay, so it doesn't matter how we permute the observation. Okay, then the rule is said to be symmetric. Okay, and we can show that for a symmetric rule, the Gini-added BDQCD and the transform one, they will have the same performance in terms of the delay and the mean time to a false alarm. Okay, so that, yeah, so I'm not gonna show you here, but we can show that. Okay, so that is for any symmetric rule, these two problems has the same performance. Okay, and for a general rule T that may not be symmetric, we can symmetrize it, and we can show that the symmetrized one will have a better performance. Okay, so that means, yeah, so that means if we want to get the optimum rule for the Gini-added BDQCD, it suffices to look at the symmetric rule. And the symmetric rule will have the same performance with this one, with the transform QCD. Okay, so yeah, so this is how we establish the connection between the Gini-added BDQCD and the transform one. So basically, we can show that they have the same optimum scaling. Okay, through these arguments. All right, so now, yeah, let's come to the final part. Okay, so we are, yeah, so here I want to compute the scaling for the transform QCD, and that will be a lower bound for the BDQCD. Okay, and here is how we do that. We just evaluate the CUSUM. Yeah, because we know that for this standard QCD, CUSUM is optimal. Okay, so we just plug in the PDF and we get this one. Okay, so this is just by definition, and you can see that, yeah. So as I mentioned, we are fixing X and summing over all the permutations, right? And this is the same as that is here that so here we are summing over all the X such that after the mapping, they will become the same X tilde. Okay, and this is the same as that we fix X and summing over all the permutation. Okay, and this is for a fixed S, and so on this term, yeah, so yeah, so this is equal to that we we fix X and summing over all the permuted assignment. Okay, so you can see that here we are fixing S and then summing over all the permuted X, and now here we fix X and summing over all the permuted assignment S. Okay, and this is the same as that we summing over all the S. Okay, so from here to here we can show that, and let me write out this term. That will become here, and yeah, you can see that the this part here is corresponding to the less n minus m honest sensor, and oh sorry, and this part corresponds to the first 2m sensors. Okay, and we can show that these two terms are the same, so they can be cancelled out, and then the only thing left is the less n minus m honest sensors. Okay, so this will help us to establish the true scaling. Okay, and I don't think I have time for showing this. Okay, but yeah, we can show that. So this is based on the same example I just chose before. Okay, so we can, yeah, so let me quickly go over this. Okay, so we can show that for each assignment S, there is a dual assignment S bar such that these two terms are the same. Okay, so here is one example. So here the S is 1 to 2 1, and under theta equal to 0, we will have this distribution, and this blue parts corresponds to this part. Okay, and under this assignment, okay, 2 1 1 2, and this is the dual assignment of this 1 2 2 1. And we can show that under theta equal to 1, we will have this distribution, and you can see that again this part corresponds to the first part, right? And they are the same. Okay, and so yeah, so that means for each term appears here, there is another S that has the same term here. Okay, and since we are summing over all the assignments, so basically we are summing over all the assignments and their duals, right? So then, yeah, so then that means these two terms are the same and they can be cancelled out. Okay, all right, and I don't have time for the second and third contribution, but we also extend this framework to the multi-hypothesis case, and in that case, the converse is the same. It's pretty much the same, and we focus on constructing schemes. Okay, and yeah, let me skip this. And for the third contribution, we use the previous results to formulate a leader follower again, and we get the optimum results. Okay, and yeah. Okay, so now let's come to the conclusion. So in this talk, I have reviewed the problem of quick exchange detection, and also we studied the BDQCD, and we proved a tight converse for the asymptotic performance of the BDQCD. And yeah, so as a corollary, we proved that one big thing suffices to be asymptotically optimal for BDQCD. And yeah, and these parts I don't have time to talk about it, but we also study the multi-hypothesis case, and also we formulate a leader follower again. Okay, I think yeah, that's pretty much it.